So now we're going to do some example problems from section 3.5. So the first thing we're going to take a look at is this, where we're going to be given some information and have to find out time to double and the amount after 10 years. The important thing to remember is this is compounded continuously, which means the equation we're going to be looking at will be like A of t equals A naught, where that's the initial investment or amount, e to the RT, where R is the rate and t is time in years. So when we're looking at this, it'd be A of t equals 2,000 e to the, don't forget to convert this to a decimal, 0.02 t. Now, that being said, when we want the time to double, it means in this particular case, we're looking for when this equation equals $4,000, aka twice the amount. Now, my argument is no matter what we're doing when we're asked to find a doubling time, is we're really looking for when the exponential portion, that is what we're multiplying by, equals 2. And if you divide both sides by 2,000, you're going to get that. Even if I bump this up to 12,000, say, that would make this 24,000 because we're talking about doubling, and I divide it, it would still be equal to 2. So in reality, when we're talking about doubling time, we're looking for when the multiple, the exponential portion, right, unmodified, is equal to 2. Now to solve this, pretty straightforward. We take the natural log because it's base e, and that will cancel out this, giving us a 0.02t equals the natural log of 2, and that means t equals the natural log of 2 divided by 0.02, which is equal to 34.657 years. Now you could translate that into months, it'd be more than 6 months, days, and months and days and that sort of stuff. But this would suffice certainly as an answer. The amount after 10 years, that's pretty easy. All you do is you find A of 10, meaning you take the exponential equation, no solving required, and plug in 10. So that would be 2,000 times e to the 0.02 times 10, which is $2,442.81. So this would be 34.657 years, and this would be 2442.81. Same question, different information. Initial investment, so we know A of t equals 1,000. E to the e, we don't know the rate. We know the time to double is 12 years, so we know that's the general equation. The time to double is 12 years. So that means that e to the r times 12, notice I'm plugging 12 in for t, is equal to 2. Can we solve this? Just like Bob the Builder, yes we can, because we're solving for r now. So we know that r times 12 is equal to the natural log of 2. We take the natural log, we divide, in this case by 12, so then we take the natural log of 2, we divide by 12, we get 0.0577. Now 0.577 as a percent is, multiplied by 100, 2 decimal places, right? 5.77%. So the annual percentage rate would be 5.77%. Now we know that this is really that, which means when we want the amount after 10 years, all we have to do is figure out A of 10. Let's do that over here, which is 1,000 e to the 0.0577 times 10, which is, 1,000 times e to the is $1,780.69. Easy. So the next one, we don't know the initial investment. We know the annual percentage rate. We know don't know the time to double, but we know how much there is after 10 years. So write as much as we know. We don't know A naught. E to the, well, we know it's 0.035 t. Okay. And we know that 10 years, which is t, right? 2,500. So we've got A naught e to the 0.035 times 10 equals 2,500. Not 25,000, 2,500. Now, can we solve that? Well, e to the 0.035 times 10 is a number. As a matter of fact, it is 1.41, make sure I write this down right, 9 times A naught equals 2,500, which means if we divide both sides, 2,500 divided by 1.419, we get an initial investment of 1,761.80. The reason I'm doing that is because it's an actual dollar amount of 61.80. Okay? That's good because it's less than after 10 years, so it can, stuff went okay. Now, time to double. Turns out time to double we could have answered in order if we felt like it, because all we're really looking for is when it's this equal to 2. In other words, the multiple is independent of the amount we started with. So, I don't know if you've noticed a trend here, but that means we take the natural log of 2, we divide it by 0.035, and that will tell us a number, which is how long it takes for this silly thing to double. So 19.804, and that would be 19.804 years. Okay? Relatively easy. All right, so this next set of questions asks about completing a table for a radioactive isotope. So this is carbon-14, right? That's the isotope. So the atomic weight is a bit off because it has more neutrons. Remember, protons define what it is, so it's a difference in neutrons. Half-life in years and an initial quantity. So what do we know? We know, let's use our P equals P naught 1/2 to the, well, what would it be? T over K, or K is the half-life. So we know that we're looking at, well, carbon-14, so we'll use C, right? C in terms of T is equal to 3 grams times 1/2 to the T over 5,730. Great, you say. Amount after 1,000 years. Well, what do? We plug 1,000 in. So C of 1,000 is 3 times 1/2 to the 1,000. Now we would expect that this is going to be more than half because this is going to be a fractional exponent, right? We're not going to be multiplying by half yet. It would take 5,730 years for that to happen. So 3 times 0.5 to the 1,000 divided by 5,730 is 2.658. 2.658, and that would be grams. So the amount would be 2.658 grams. Pretty easy if you use this half-life formula. Okay, here's the half-life. So this is plutonium-239. This is the, I believe the, yeah. Plutonium, this is enriched uranium, right, which becomes then plutonium. Half-life 24,100 years. They use this in atomic bombs. Initial quantity, we don't know. Amount after 1,000 years. So what do we know? We know that P of T, right? There we go, equals, we don't know, some amount of plutonium initially times 1/2 to the T over 24,100, right? Okay, we have a data point. We know that after 1,000 years, we've got 0.4 grams. This whole mess is just a number, 0.5 to the 1,000 divided by 24,100 is a number. As a matter of fact, it is 0.971. So we divide both sides, and the initial amount of plutonium is 0.4 divided by 0.971, aka 0.411 grams. Not much more than after 1,000 years. But if you look at that half-life, not much has gone away at that point. So it makes sense. Okay, for these next one, they want you to write this model, which is a continuous model, that fits this. Now I'm going to go ahead and I'm going to boldly write, well, let's see what we can pull off. There's a couple different ways to approach this. One is you could write this model, and remember that this A and this A are the same thing, right? And they end up being the y-intercept in non-shifted models, and it looks like we have a y-intercept, right? And this is the multiple. We know that this B here is, in reality, this e to the B here. So here's what we can do. We've got our 2 points, yes? So then we can recognize that it's 0, 1. So we're going to go ahead and just plug this in. So we're going to plug in 1 for y, and then A, e to the B, 0. So what does this tell us? What is B times 0? It's 0. What is e to the 0? 1. A equals 1. All right, that was tough. Now we're going to use this point, 4, 5. We're going to use this point. So this first thing we use 0, 1, plugged into the equation. Now we're going to use 4, 5, knowing what we know, which is that we know A is 1. So we know 5 equals 1 times e to the, we don't know B, but we know that this is 4. Is this an equation we can solve? Well, the 1 isn't inconsequential in this case. We could divide by 1, we still get 5. So really, we got e to the 4b. So what we can do is take the natural log of both sides, and when we take the natural log of both sides, that cancels out, so we get 4b equals natural log of 5. B is the natural log of 5 over 4. Because they want it in this form, it turns out this is probably the easiest way to go. So what does that mean? The natural log of 5 divided by 4 is 0.402, 0.402. So our equation in the end, I'll do it the other way here in a sec. The equation in the end ends up being y equals 1, I'm not going to write it, e to the 0.402t. That's it. So for this one, what I'm going to do is recognize that this is a y-intercept. And because it's an unmodified graph, I know that I'm looking at y equals 1 times b to the x. I know that's not the right formula. Give me a sec. So I know then that if I plug this in, that 1/2 equals b cubed. How do I undo that? So this is another way to go, by the way. I could take the cube root. So what is the cube root of 1/2? What number times itself 3 times equals 1/2? We're about to find out. B, that is the multiple, equals the cube root of 1/2, aka 0.793. This is not the same b as up here, but we do know that this b and the y equals b to the x thing is the same as the, well, if you look at this carefully, this b and this e to the b are the same thing. So we know that e to the b equals 0.793, that is what we're multiplying by, which means b equals the natural log of 0.793 negative 0.231. Now do not be distressed. It does mean that our final answer is e to the negative 0.231 t. With this value of b, it means that we're multiplying by something less than 1, which is, as a matter of fact, is right around 21% decay, right? Turns out that because if we're looking at this model, negative exponents with continuous change end up being decay, and so we're still getting decay. so everything's okay. All right, marketing, sales, and so they give us this equation, and then they say when $500 is spent, 2,500 units are sold. Okay, $500 is X, $100, X $100, X $100. So if we're talking $500, that is 5 hundreds, right? So X would be equal to 5 after X $100 is spent. How many $100? $500. So that means X equals 5. So $500 translates to X equals 5. This is kind of important. Now S, 2,500, in thousands of units. So 2,500 units is 2.5 thousands of units, right? This is kind of important because you get to translate what these things meant, because it says the units here are in thousands of units. So this means we're looking at 2.5 equals 10 times 1 minus e to the k times 5. Now, complete the model by solving for k. Hey, if I plug that information in, that particular data point, I'm good. So then what? Well, let's divide by 10. So that's going to be 0.25 equals 1 minus e to the k. I'm just going to say 5k. It's a little easier, right? E to the 5k. Then I'm going to subtract 1, which is negative 0.75 equals, don't forget that negative, right? Stays with the e. Divide both sides by negative 1. I'm going to take the natural log. And then I'm going to divide by 5. So k ends up being the natural log of 0.75 divided by 5, or negative 0.057. Okay. So what does this mean? When $500 is spent on advertising, 2,500 units are sold. 10 minus, all right, well, let's see if this makes sense. So now we know that our model proper is S equals 10 times 1 minus e to the negative 0.057 x, right? And now they want to know $700. If we bump up our advertising expenditures to $700, the problem is that is x equal to 7. So it means that we're going to plug in 7 in for our x and figure out how many units we sold. So this is a matter of typing this in correctly more than anything else. E to the negative 0.057 times 7 is 3.290. Now remember, this is thousands of units. So that's 3,290 units. Now let's see if that makes sense. $500 got us 2,500 units sold. It would make sense that the more we spend, the more units we sell, which we do. So what I'm saying is our answer is actually reasonable, even though we had exponential decay here, which maybe doesn't make any sense, but it's 1 minus, right? So it's been reflected and shifted, right? Sound familiar at all? Anyway, but that is indeed what we're doing. All right, this last one, now I've already done the graph here. Number of yeast, Y of yeast organisms in a culture is given by the model, this. So this is a logistic curve, and these are used to represent bounded situations, particularly for growth or populations, that sort of thing. Think of like spreads of information. It starts off when few people know, but then it grows, and as more people know, it goes really rapidly. But then at some point, there starts to be a point where fewer people, or a bunch of people already know the information, so the rate decreases until eventually everyone knows it, and that means it levels off, okay? So there's our graph of the model, where this would be Y, the number of yeast organisms, and this would be T, and this is in hours, right? Okay, Use the model to predict the populations for the 19th and 30th hour. So that would mean we're going to plug in 19 into this equation. And come up with a number, and we're going to repeat that for 30. Now I'm going to leave that up to you. I think it's possible for you to just plug in the numbers. So plug in 19, plug in 30, write down how many yeast organisms. I would strongly recommend that you go to the nearest whole yeast, because fractional yeast, think about that poor yeast, right? According to this model, what's the limiting value of the population? Well, in a logistic model, the numerator ends up being the limiting value, and if you actually have graphed this out yourself, turns out this value that it levels off at is 663. So the limiting value is 663 yeast organisms, as shown by the 663 in the numerator. Why do you think this population of yeast follows a logistic growth model instead of an exponential growth model? Well, why? So if you're talking about yeast organisms in a culture is a growing medium, agar or something like that. And so what that means is yeast requires food to probably get its energy and then divide and grow and all this sort of stuff. Is it possible that it eats up the food, being it's a closed system, right? So it's sitting there in this petri dish or whatever. So why does this make sense that it levels off? Because eventually the food runs out. Which means there's a limit. This particular petri dish with this amount of culture in it, that is food for the yeast, if you will, can only sustain so much of a population. This is also true of things like planets and stuff like that. So there is a limiting factor to the population of just about everything. So this concludes our examples from section 3.5.